Hello, Physics 30s. In today's lesson, we are going to finish the unit of study on magnetic forces and fields, and we're going to do that by concluding our discussion of electromagnetic induction by talking about another law that is really important to properly understanding the process of electromagnetic induction, and that law being called Lenz's law. Learning outcome for this lesson is identical to the one from the last one. We're just going to continue to build a qualitative understanding of electromagnetic induction. This time around, we're not going to deal with it quantitatively in any fashion at all. Lenz's law states that an induced current flows in such a direction that the induced magnetic field it creates opposes the action of the inducing magnetic field. Okay. This statement is really, really confusing. The reason this statement is so confusing is because there are three different things that are actually occurring in the statement. There's a reference to something called an induced current. There's a reference to something called an induced magnetic field. And there's a reference to another thing called an inducing magnetic field. And to properly understand Lenz's law, we need to break this down into three different parts. And we're going to approach Lenz's law by looking at a very specific example that we're already quite familiar with. That being the case where we have a solenoid, stationary solenoid, and I'm going to take a bar magnet and move it close to the solenoid. This is pretty much identical to both the activity performed in the mini lab and also experiment 1 from the last lesson. The only difference is that the solenoid is being wrapped around a ferromagnetic core as opposed to the region inside the solenoid being totally empty. It's going to make it easier to explain the Lenz's law if we do actually wrap the solenoid around a ferromagnetic core, but otherwise the scenario is going to be identical. All right, so let's bring this bar magnet close to this solenoid. When I do that, you're going to induce current in the solenoid as a result of the motion of the bar magnet. We know that we can only induce motion in that solenoid as long as there is relative motion between the solenoid and the bar magnet. As long as we keep the solenoid stationary and move the bar magnet, there's definitely a relative motion between the two. Faraday's law tells me that you will induce current in a conductor as long as you can change the magnetic flux through an enclosed area. So just to quickly review why you are changing the magnetic flux through the solenoid. So let's take the enclosed area, which is just the wire cross section. Okay, so this circle represents the wire cross section. And just like last time I said, pretend that you're on that wire cross section and you're counting the number of magnetic field lines that pass through there. Well, as you bring that bar magnet closer and closer to the solenoid, as the pole gets closer to that solenoid, you're going to have an increasing number of magnetic field lines pass through that enclosed area. If the number of magnetic field lines through that area is increasing, then the number of field lines is changing, and that means your magnetic flux is changing through that enclosed area. If the flux changes through that enclosed area, then you do indeed induce current in the solenoid. After you induce current in the solenoid, well, then you have a current-carrying wire. And if you have a current-carrying wire, we know a current-carrying wire with moving charges produces its own magnetic field. So the solenoid is actually going to produce a magnetic field. So the induced current in the solenoid is then going to produce an induced magnetic field. Now, we would use the second-hand rule to predict, well, what is the direction of the induced current in that solenoid? The problem is, without Lenz's law, we don't know what direction it is. For example, we know that the current is going to be induced as I bring the bar magnet close by, but I don't know if the induced current is going to be from A to B or if it's going to be from B to A. And this is where Lenz's law is going to help us out. Now, in a nutshell, what Lenz's law tells you is that when you induce current in this conductor, it's going to generate a magnetic field. And when it produces a magnetic field, it's always going to be produced in a way that's going to oppose what you were attempting to do. So what I'm attempting to do in this scenario is I'm attempting to move this bar magnet close to the solenoid. That's what I want to do. Lenz's law tells you that when this bar magnet, the motion, induces current in this solenoid, that this solenoid is going to make a magnetic field that then opposes the motion of the original bar magnet. So what I want to identify here is, okay, so if there's a magnetic field produced by the solenoid, it's going to induce polarity on this ferromagnetic core. Now, if I look at this end of the bar magnet inside of the solenoid, in order to oppose the motion of this bar magnet, what pole would this need to be? Well, if I wanted to slow this thing down, I would need this pole to be a north pole. So let's draw that. This is a north pole, and then this would be a south pole. That's my implementation of Lenz's law. So as I bring this bar magnet close, you'd be asking yourself, well, how do I know which is a north pole, which is a south pole? You're always going to set up a magnetic field so that the motion of the original object is going to be opposed. So the only way I can oppose the motion of this is for this right end of the bar magnet inside the solenoid to be a north pole. And that's what I've set up here. The induced magnetic field of the coil will oppose the original inducing magnetic field. We'll distinguish between what those words mean in a moment, between induced and inducing. Well, now that we have the polarity of that bar magnet in the solenoid, we can then figure out what the direction of the current is through the solenoid. And we can do that using the second-hand rule. So the way we would use that is, let's go to our second-hand rule. And we'll do current. So if it's current, we're going to use our right hand. In the second-hand rule, the direction of the magnetic field is represented by the direction that your thumb points. Your thumb is going to point in the direction where you're going to have an induced north pole. So the direction of the magnetic field within the solenoid would be towards the right. The direction of the induced current, well, it's going to be circular because the solenoid is loops of wire. That's going to be the direction of the curl of your fingers. All right, so the way I would apply the second-hand rules, again, this is easiest to do if you just take a pencil to like wrap your fingers around. So if you take your right hand and you just have your thumb point towards the right, and then you take your fingers and wrap it around a pencil. What I want to do is I want to look to see if my fingers are wrapping from behind the pencil or over top of the pencil. And if you do this correctly, with my thumb pointing towards the right, with my right hand, my fingers should be wrapping from behind behind your pencil or from behind the ferromagnetic core. The direction that your fingers wrap from behind tells you how the wire starts off by wrapping. So since my fingers wrap from behind, well, let's look at the solenoid. So which part of the solenoid has the wire wrapping from behind first? Would it be the side A or the side B? Well, it's the side A. The side A has the wire wrapping from behind. So what that means is that's going to tell me what direction the current is initially moving. So the current is going to be going in this direction, which will be from A to B. Let's summarize that. According to Lenz's law, if I need to slow down the motion of the original conductor, then there needs to be an induced north pole on the right end of this bar magnet within it. If I use a second-hand rule then to figure out the direction of the current would flow from A to B. Now, in this problem, I don't have this wire connected to anything. In fact, it's not even a complete circuit. The wire is broken from this portion A over here over to B. So I can't actually generate a continuous current. But what I can do is I can polarize the wire. The direction of conventional current tells me the direction that quote unquote positive charge would go. Again, I'm totally aware that like positive charges cannot move. So what this would mean is that I would polarize the wire in a fashion that would make side B positive, because you're pushing all of your conventional current or positive charges there. If you move all the positive charges to the right end of the wire, that would leave the left end as a negative side. Therefore, side A would be negative and side B would be positive as a result of the induced current polarizing the wire. Now, let's take a step back and go back to the statement of Lenz's law. And let's talk about, in this problem, what was the induced current, what was the inducing magnetic field, and what was the induced magnetic field. Okay, so when I'm going to induce current in a conductor, we typically go through the following steps. So 1, there is the action of what we call the inducing magnetic field. The inducing magnetic field would be the object that is getting things started. It's getting things going in the first place. So what got things going in the first place? Well, that was the bar magnet we were moving. That was the bar magnet that we are moving towards the left with a specific velocity. That bar magnet has aligned domains. It's a ferromagnetic material. It produces its magnetic field. We call it the inducing magnetic field because it's going to be the thing that gets things going. 2, as a result of the inducing magnetic field from the bar magnet, you're going to induce current. And you induce current in accordance with Faraday's law. Where's the induced current? Well, it's the induced current in the solenoid. And again, you induce current because there's a changing magnetic flux through the cross-sectional area of the solenoid. I don't know if I should call it the cross-sectional area of the solenoid, just the circular area, the circular enclosed area of the solenoid. 3, we have the induced magnetic field. The induced magnetic field is the one that's created by the induced current. Well, once you get current running through the solenoid, then the induced current in the solenoid produces its own magnetic field. And that would be the magnetic field that's produced within the solenoid or within the coil. And it's that induced magnetic field that is going to induce the polarity on that bar magnet. Now, let's look at the opposite scenario. So what we observed in the mini lab is that if you pull the magnet away in an opposite direction, you actually will induce current in an opposite direction. On the digital multimeters, it would have represented this as current being positive in one scenario and current being negative in the other scenario. The negative current just means the current is moving in a reverse direction. Okay, so let's try to apply Lenz's law to this. And this is how I would do it in terms of like how I would approach a Lenz's law type problem. All right, so what am I doing here? Well, I'm taking the bar magnet and I'm moving it towards the right. So I'm moving it away from the actual solenoid. What Lenz's law tells me is that as this guy moves away, it's going to induce current in this conductor. This current induced in the solenoid is going to produce a magnetic field, but it's going to produce it in a way that always tries to oppose your motion. So what am I trying to do here? Well, I'm trying to get away from the solenoid. So what pull would this end need to be to oppose my motion? Well, it would need to be a south pole, because the attraction between the south and north pole would slow this bar magnet down. That means that this would be a north pole. And if we go through the exercise of the hand rule again, try to figure out what direction of current. So once again, current would be right hand. And with the second hand rule, the magnetic field is represented by the direction that your thumb points. In this situation, the north pole is on the left end. That's the direction the magnetic field lines would point in the solenoid. Again, the magnetic field lines need to come out of the north pole. So that's why your thumb would point in that same direction. So that would be towards the left. To figure out the direction of the induced current, then what you would do is you would use the curl of your fingers. So I take my right hand and I point my thumb towards the left. Take your fingers, wrap it around a pencil. Now look at how your fingers are curling this time. Are they wrapping over top of the pencil, or are they wrapping from behind it? And if you do this correctly, your fingers should be wrapping over the top. So which part of the wire is it initially wrapping over the top at? Part B or part A? Well, it's part B. At part B, I can see the wire wrapping over top of the actual solenoid. So in this case, the direction of induced current would be going from A to B. Oops. Let's label that as current, not B. And what this means is the direction of conventional current would be the direction that hypothetically positive charges would go, which means that I would accumulate positive charge on side A, and that would leave side B as being negative. I should point out, by the way, that you could actually use you could get the exact same result if you just looked at the direction of electron flow. So if I change this for a moment, and this is why we still use conventional current, because you might be like, why don't we just use electron flow because that's the correct model? Well, it doesn't really matter here. So let's say we changed this so I wanted the direction of electron flow. So the direction of electron flow would then just be using your left hand. So let's see what happens here. If I used my left hand with my thumb pointing towards the left, the curl of my fingers would be wrapping from behind. So where does the wire initially wrap from behind? Well, it wraps from behind at this side. So what that would tell me is it would tell me the direction of electron flow is just in the reverse direction. And what does that do? Well, if the direction of electron flow goes from A to B, you'd build up negative charge on side B, and a deficiency in electrons would leave side A as positive. So you get the exact same result whether you use left hand for electron flow or you use the right hand for conventional current. Now, before I move on, I just want to talk about why this happens. Why is it that when you have this bar magnet either move towards or away from the solenoid that your motion is always opposed? Okay, so let's go back to, let's just do this picture. And I'm just going to erase everything. Okay, so let's say that I bring this bar magnet close to this solenoid. And let's identify. Let's say we have, like, start off with it's moving, and we start off with 20 joules of kinetic energy. As this bar magnet gets closed, again, Lenz's law would tell me that I'm going to induce a magnetic field that opposes the motion of my original bar magnet. So that's a north pole. What that's going to do is that's going to slow this bar magnet down. So maybe it slows it down to 18 joules. So the immediate question would be, well, what happened to 2 joules of my energy in terms of conservation of energy? Well, the 2 joules of your energy would be given to making current. I suppose we could call that electric potential energy. So we'd have 2 joules. So what's happening here is, like, your input energy was 20 joules. Lenz's law forced you to slow down. And the reason it forces you to slow down is if you slow down, you've lost some kinetic energy. Well, where did that missing kinetic energy go? Well, it was used to generate current inside of the conductor. Inside of the conducting wire. Now let's consider what happened if, like, the opposite was true. So let's say that you brought this close and the pole was induced to help you out. It made you move faster. Like, let's say this was a south pole. Okay, this is not actually a south pole, but let's just consider the counter argument here. So let's start off with EK as 20 joules. And if this is a south pole, that'd make me speed up. So I would turn this into, like, for example, 22 joules of kinetic energy. Immediately, this makes no sense. Like, you can't start with 20 joules of kinetic energy and then mystically just gain 2 joules of kinetic energy, and also, in the process, give energy to this guy. Because what this would tell you is that your input energy is 20 joules, and your output energy would be 22 plus 2, which is 24 joules. So you'd be violating conservation of energy. So really, when it comes down to it, like, what is Lenz's law a statement of? It's really just a statement of conservation of energy. So the motion of, like, your original bar magnet is always going to be slowed down because it needs to lose some of its kinetic energy to give it to the solenoid. Talked about a lot of hand rules. So the first hand rule applies to a straight current carrying wire. Second hand rule to a solenoid. We talked about a couple different hand rules. We talked about the first time we talked about the third hand rule was a single moving charge through a magnetic field. Then we had the third hand rule for a wire with current moving through a magnetic field. Then we talked about the modified third hand rule, which is when we had a wire that we physically grabbed and moved through a magnetic field. We can actually take all those hand rules and just combine them into a single hand rule if we just make the way that we identify parts for a hand a bit more generic. So here's how we could do this. Regardless of whether you're using the third hand rule for a single charge, current carrying wire, or for electromagnetic induction, your fingers always point in the direction of the magnetic field. So that's a constant. Your thumb, well, in the case of a moving charge through a magnetic field, your thumb is the velocity of the particle. For a current carrying wire, it's the direction of current. And for the electromagnetic induction effect, it's the direction that you grab and physically move the wire. We can actually classify all of those three descriptions just by calling it the input. Like, what are you putting into the actual system? The direction your palm faces is your output. So your output for a single charge through a magnetic field, moving charge, or a current carrying wire is always a deflecting magnetic force. In the case of electromagnetic induction, your output would be induced current. So let's look at this for example. So the top diagram is I have a current carrying wire showing the direction of electron flow moving through a magnetic field. So if I want to classify things as input or output, well, for the top diagram, your input would be the direction of electron flow or current. So that's the direction my thumb would point. Your output would be the direction of the magnetic deflecting force. For the second diagram, we are physically grabbing this wire and pulling it through a magnetic field. We grab this wire and pull it through a magnetic field, then my input would be the velocity of the wire. The velocity of the wire is the result of me moving it. And your output would be the direction of induced current. Just want to point out, by the way, so for this case, so again, this is only like part of a wire. It's not a complete wire. So once again, if you don't have a complete wire, you can't get continuous current. You would end up just polarizing the wire. So let's just go through this. I'm not going to write this down, but let's say I want to figure out which side is positive and which side is negative. Well, let's use this combined third-hand rule. So the input is the direction of the velocity of your wire. So I take my right hand, if we're going to do current, and I point my thumb towards the top of the computer screen or top of the page. I would then take my fingers, making sure they're perpendicular to my thumb, and point them in the direction of the magnetic field. So that would be towards the right side of the page. So my fingers point right, my thumb points towards the top of the page. If you do this correctly, the direction that your palm faces should be into the page. It should be facing into the computer screen. So that would tell me that the direction of induced current would be from A to B. If induced current goes from A to B and the wire is broken, I would just polarize the wire. So if induced current goes to side B, this side would become positive and side A would become negative. All right, just one more quick question dealing with how we can apply Lenz's law. So this is one of the examples we dealt with last time. So we had a complete circuit and we pulled this thing through a magnetic field and we wanted to determine what the direction of the induced current was. Now, it turns out that Lenz's law also applies to this situation. It applies to any scenario where you have current being induced. Okay, so let's try to figure out how this would actually work step by step. So let's worry about, first of all, this will be a bit of a repeat from yesterday, but let's just worry about the direction of the induced current. Okay, so let's do induced current. So we use the third hand rule, which would tell me that the fingers point out of the page. The input, which is my velocity, would be towards is the direction my thumb points. And that would be towards the right. And then the direction of induced current would be my output. And that's the direction that my palm faces. And the direction your palm face should be towards the bottom of the page. Again, if you take your right hand, take your thumb, so it's perpendicular to your fingers. If your fingers point out of the page and your thumb points towards the right side of the page, you really got to contort your wrist to do this, then your palm should be facing towards the bottom of the page. Okay, so what I would have here is I would have current. Again, you induce current in the magnetic field. That goes in a direction that would be clockwise. And again, we went through this last time. Now, here's what happens. After you get current, so now what I've done is I've induced current in a magnetic field. So I now have moving current through a magnetic field. So it's now like I have a current carrying wire. There's a current carrying wire through the magnetic field. If you have a current carrying wire through a magnetic field, that wire is subjected to a deflecting force. So let's look how this would play out. As a result of inducing current, I now have a current carrying wire. Okay, so we can use a third-hand rule for a current carrying wire, which would tell me that B, your fingers, again, this is the one constant, is once again out of the page. For a current carrying wire, your current is represented by the direction that your thumb points. And we're just going to focus on this branch of the wire. So in this case, your current, your thumb is pointing towards the bottom of the page. A current carrying wire will be subjected to a magnetic deflecting force, which is your output. So your input here would be your thumb, which is the current. Your output is your palm, which is the deflecting force. Okay, let's use the third-hand rule to predict what direction this would be. Take your thumb and fingers, make sure they're perpendicular to each other. Have your fingers so that they are pointing out of the page. Take your thumb and point it towards the bottom of the page. And again, you have to contort your wrist quite a bit to do this. So if you have your thumb pointing towards the bottom of the page and your finger is pointing away from the computer screen towards you, the direction of the magnetic deflecting force should be towards the left side of the page. So what this means is on the wire, there would then be a magnetic deflecting force that is towards the left. Well, look what I was trying to do. I was trying to take this wire and move it towards the right through a magnetic field. What Lenz's law tells me is that as a result of the action of the inducing magnetic fields, the inducing magnetic field would just be this magnetic field we see here with the 16 dots. The inducing magnetic field will induce current. So I got some induced current that on this segment of the wire is towards the bottom of the page. The direction of this induced current is always going to be set up in a way that opposes the direction of what you're trying to do. So I'm trying to move the wire towards the right, and as a result of inducing this current, I end up getting a deflecting force towards the left. So the wire or the circuit is going to be slowed down as a consequence of Lenz's law. And again, there's got to be a cost here, right? Because if once again you started off with this guy moving at 20 joules of kinetic energy and you induce current in the wire, so maybe I induce current in the wire of 2 joules, you have to lose some of that kinetic energy. So again, your motion is always going to be opposed. So that's the interesting thing about electromagnetic induction is like, yeah, we can induce current as a result of motion through a magnetic field, but at a cost. So the cost always being whatever input energy I'm putting in, like that kinetic energy, our motion's always going to be opposed. We're going to lose some of that kinetic energy because some of it has to go to providing electric potential energy to induce current in the wire. All right, so that's it for the unit on magnetic forces and fields. If you'd like, you can practice some problems dealing with Lenz's law and electromagnetic induction on an assignment called Lenz's Law Hand-in assignment. And I will talk to you in the next unit of study on light and optics.